So dear students, now let's begin with the application of CFT to tetrahedral. All of you know in tetrahedral complexes, there is a central metal ion and its coordination there is 4. That is, 4 ligands are attached to the central metal ion. Now let's begin with the arrangement of these 4 ligands around the central metal ion. In tetrahedral complexes, metal ion is present at the center of the cube. Okay, this is the metal ion is present at the center of the cube and 4 ligands are approached from the 4 corners but alternate corners of the cube. That means suppose if one ligand is approaching from this corner, then other ligand will approach from alternate. This, then leave this, one ligand will approach from this, then this, leave this, one ligand will approach from this and other ligand will approach from this side. So, we will see tetrahedral complex in cube like this. So, in tetrahedral complex, metal ion is present at the center of the cube and 4 ligands approach from the corners, alternate corners of the cube. While the direction of x, y and z axis, it is from the center of the faces of the cube. See here, this is y-axis and it is going from the center of this face, x-axis and y-axis. So in tetrahedral geometry, this diagram, it shows tetrahedral geometry having central metal and 4 ligands at the 4 corners. All of you know there are 5 d orbitals. Okay, that is dz square, dx square minus y square. These are called as Eg orbitals, and dyx, zx and dx. These are called as T2g orbitals. Okay. Simply in tetrahedral complexes, they are called as E and T2. Just remember. Now all of you know E orbitals, that is dz square and dx square minus y square. Their lobes are along the axis, or they points along the axis, while T2 orbitals, these 3 T2 orbitals, their lobes are present in between the axis. Okay? These are along the axis and these are in between the axis. Actually, in tetrahedral complexes, just saw that ligands approach from the corners, alternate corners of the cubes. And it is observed that the direction of ligand, though they do not directly coincide with any of the orbital. They do not directly coincide either with the E or T2 orbital. But as ligands are approached from the corners of the cube, the T2 orbitals are more closer to ligands. And as two orbitals are more closer, they experiences more repulsion, and hence in case of tetrahedral complexes, T2 orbitals, their energy increased as compared to E orbitals. Here you can see the energy difference or the crystal field splitting of tetrahedral complexes is exactly in opposite way that we have already discussed in octahedral complexes. All of you know in octahedral complexes, 3 T2G orbitals, their energy is lower as compared to 2 EG orbitals. But in tetrahedral complexes, as ligands are approached from the corners of the cube and T2 orbitals, they experience more repulsion. That's why their energy is increased and E orbitals, their energy decreased. Now these increase and decrease in energy will explained in this diagram for tetrahedral complex. See here are the d orbitals of free ions. All are degenerate d orbitals of equal energy. When d orbitals comes in the spherical crystal field, then their average energy slightly increase. But when these d orbitals comes the tetrahedral crystal field, then it undergoes splitting. D orbitals undergo splitting, and 2e orbitals, their energy is decreased. Out of 5d orbitals, 2d orbitals, their energy increased as compared to 3d orbital. So their energy is by 3 by 5 delta t, while 3t2 orbitals, dxy, dyz and dxz, out of 5, these 3 orbitals, their energy is increased as compared to the 2d orbitals. That's why their energy is by 2 by 5 delta t. See, we can write down 2 by 5 is total, it is 10. All of you know is a 10 delta t, just like TQ. So 2 by 5, simply we can write down their energy is increased by 4, and here it's by minus 6. Or we can write down 0.4 delta t, and it can write down minus 0.6 delta t. Energy is decreased by minus 0.6 delta t. Now, the T2g orbitals and EG orbitals, their splitting we just discussed. The magnitude of crystal field splitting of delta T in tetrahedral complexes considerably less than in an octahedral complex. We know that crystal field splitting in tetrahedral complexes delta T and in octahedral complexes delta O. But the splitting, the distance in delta O, it is greater. In delta T, though there is a splitting, but distance here in this diagram, this distance is more as compared to this distance in delta T. So the relationship delta T and delta O shown by this relationship that delta T is equal to 4 by 9 delta O. Now, one more interesting thing you need to remember that tetrahedral complex always high spin complex, because generally tetrahedral complexes are formed by weak ligands. And that's why in tetrahedral complexes, as the ligands are weak, the splitting is always less than the pairing energy. In tetrahedral complex, pairing is very high. So instead of get paired, electron always prefer to get excited in higher energy level. And as electrons are excited, tetrahedral complexes are high spin complex. For the calculation of tetrahedral complexes CFSE, we can use this formula. These formula are almost similar that of CFSE in octahedral complexes. Only thing here, EG orbitals, their energy increase, and T orbital, T orbital, their energy increased, and T orbital, their T2, their orbital. This formula we will here use. We'll discuss it later. Now, just see which conditions are favorable for tetrahedral complexes. Just now I explained that tetrahedral complexes are always high spin complexes. Why they are high spin complexes? Because the most important thing, tetrahedral complexes are formed when ligands are weak, or when the ligands are larger in size, bulky, and could cause more crowding in octahedral complexes. and they cannot get accommodated in octahedral complexes, because in octahedral complex 6 ligands are. So they prefer to go for the tetrahedral complexes, or when central metal has lower oxidation states. And the fourth favorable condition for tetrahedral complexes is when the metal has electronic configuration like D0, D5 or D10. That means empty half-filled d orbital or completely filled d orbital. In such cases, CFSE is, or when D1, that means one unpaired electron, or D, then CFSE is low. So all these conditions they favor for the tetrahedral complex. One thing you need to remember, tetrahedral complexes are high spin complex. Okay. Now in next video, we will solve some problems based on calculate CFSE and magnetic properties of tetrahedral. Thank you all of you.